Today we are going to solve questions from the year 2021, and this is part 1 for the year 2021. Here we are going to solve total 10 questions, and all these 10 questions are from the mains part. So the first question, it states that 27 similar drops of mercury are maintained at 10 volt each. All these spherical drops combine into a single big drop. The potential energy of the bigger drop is dash times that of the smaller drop. So we are given that we have mercury drops which are small. Let us suppose each is having a radius of r, and these are 27 in number, and they combine and form a bigger drop. Let us suppose the radius of bigger drop is capital R. So we can find out relationship between the smaller and bigger drop, radius of bigger and smaller drop. You can say the volume of bigger drop, will be equal to 27 times volume of small drop. Volume of small drop. And so for bigger drop we can write this as 4 by 3 pi r cube is equal to 27 times 4 by 3 pi small r cube. 4 by 3 pi cancels out, and we get from here that the capital radius, that is of our larger sphere, radius r, is equal to 3 times that of small r. And we are interested in finding out potential is given as 10 volt, and so let us deal with that. And we are given that potential of a spherical conductor, the formula we already know, so we can write that potential energy of a spherical conductor and suppose its radius is of radius capital R and charge Q. So we can write our U will be equal to, this comes half, and Q square upon 4 pi epsilon naught multiplied by R. And since we are given potential. So we can write also that the potential, which is our V, it can be written as 1 upon 4 pi epsilon naught, and this becomes Q upon R. So from here we can find out our Q will be equal to, we get this as 4 pi epsilon naught times R and multiply by V. We substitute this value of Q in the energy equation. Therefore, we can write that our energy U will be equal to over half. This comes as our 4 pi epsilon naught R whole square V square, and this is 4 pi epsilon naught, and we have this is R. And let me write it a little bit different way, because this way it will be easy. So this comes square and here becomes our R square. So this 4 pi epsilon naught cancel with this square, R square goes by square, and ultimately 4 goes by 2. So we get the energy will be equal to 2 pi epsilon naught R, and we have this as V square. So this is the general expression for the energy. Therefore, from here we can at least say that our potential energy is proportional to R, given that our potential is constant, because all the terms 2 pi epsilon naught is constant. So our energy will be proportional to R, given that the value of our voltage, that is potential, that is given as V, is constant. And also, as the drops are combined, the charge is added, radius is also going to change. Accordingly, the potential is also going to change. Okay, so we have to remember that thing. And for the smaller drop, you can see for small drop, let us suppose that the charge is our small q. Therefore, we can write that the potential energy is proportional to q square upon r. And for bigger drop, our total charge if it is given as capital Q, that will be equal to 27 times small q. And we just found out that radius of the bigger drop is 3 times the smaller drop. So you can see radius, which we have taken as capital R, is 3 times the smaller drop. So we can write that the energy associated with the big drop will be proportional to our q square upon r. And we substitute this as 27 q whole square, and this comes as our 3r. So we can write this will be coming as 729 Q square divided by 3R, which gives us 243 times Q square upon small r. And this Q square upon small r is nothing but our energy of the small drop. Therefore, we can write that our energy of the big drop will be equal to 243 times energy of the small drop. Okay. And I think this was, yes, so this comes as 243. Next question. We are given, find the electric field at point P as shown in the figure on the perpendicular bisector of a uniformly charged thin wire of length capital L carrying a charge Q. The distance of point P from the center of the rod is A, which is given as square root of 3 times L divided by 2. So we have to find out the electric field at point P. This is point P and it is uniformly charged carrying a charge Q. So this entire rod is carrying a charge Q. So we can draw this figure once again. So we can just it is given a perpendicular bisector. So we have a perpendicular bisector. Point P is somewhere here. So this will be over L by 2 and lower portion will be also L by 2. And this is center of O given as 90 degree. And we can just join these two parts. And we are okay, and this distance is given as A, which is given separately as square root of 3 L divided by 2. And from here we can say that our this distance will be our L square by 4 plus A square and its square root. Similarly on the bottom side also L square by 4 plus A square and its square root. Let us suppose the angle made by them is our theta, and total charge is given to us as Q. So let us assume that this rod is having a charge density of lambda. So we can say that rod is having a charge density which is our lambda. So this lambda will be equal to our total charge divided by total length, that is our L. And we can solve this. It will be A is given to us, so let us sort it out. So this comes as L square by 4 and we have this as our A square. A square will be our 3L square by 4 and its square root. So this comes as 4 by 4, which gives us L. So similarly this will be also by L. Okay. And from here we can find out our sine of theta. So we can say sine of theta will be equal to our 1 by 2. And our net electric field will be along this direction, so let us call this as E net, and we can say our net electric field formula is a quite standard one, and we can write that our net electric field that is our E net will be equal to lambda upon 4 pi epsilon naught, and here the perpendicular distance is A, and we have this as sine of theta first angle plus sine of theta, that is our second angle. So we already know all the values, we can just substitute them. We get this will be equal to our lambda is our Q upon L, so we can write this will be equal to our Q, and this comes as 4 pi epsilon naught. A is our root 3 L by 2 L upon 2, and sine of theta sine of theta is 1 by 2, so this comes 1 by 2 plus 1 by 2, and we can write it as this will be coming to theta, and we have this as 4 pi epsilon naught square root of 3 and L square, and this will give me as 1. So this 4 goes by 2, therefore our net electric field E net will be equal to Q upon 2 root 3 pi epsilon naught L square. So this is the net value of the electric field. So we get this as option number 1 is correct. 1 is correct. Next question. It states that consider the combination of two capacitors C1 and C2 where C2 is greater than C1. When connected in parallel, the equivalent capacitance is 15 by 4 times the equivalent capacitance of the same connected in series. Calculate the ratio of capacitance of C2 by C1. So first they are connected in parallel. So we can see equivalent capacitance in parallel. Equivalent capacitance in parallel. Let us call this as Cp, which will be equal to our C1 plus C2, and then they are connected in series. So we can say equivalent capacitance in series and we can write this as Cs will be equal to C1 times C2, C1 plus C2, and we are given that the 15 by 4 times the equivalent capacitance of same when they are connected in series. So which basically means that our Cp will be equal to 15 by 4 times our Cs. So we get this C1 plus C2 is equal to 15 by 4 times C1 C2 and C1 plus C2, and we can just cross multiply them. We get this as 4 times, this comes as C1 plus C2 whole square is equal to 15 times C1 C2, and we can just open the bracket. We get this as 4C1 square plus 4C2 square plus 8C1 C2 is equal to 15 times C1 C2. So this is going to give us a quadratic equation, and we can write this as our 4C1 square plus 4C2 square, and this will be minus 7 times C1 C2 is equal to 0. So we can just convert into a one variable and substitute with the other one. Okay, let's divide the entire equation by C1. So this is C1, or rather C1 square, and this is also C1 square. So C1 square cancels out. Here square goes by this C1. So we get from here that we can write this as 4C2 by C1 whole square minus 7C2 by C1 plus 4 is equal to 0. And let us assume that C2 by C1 is our x. You can say let C2 by C1 is a variable x. So we get this quadratic as 4x square minus 7x plus 4 is equal to 0. And this question is basically, you can say, the roots will be coming as negative, because we find out if b square minus 4ac, and this gives us our 49 minus 64, which will be coming less than 0. Okay. So therefore this question was basically a bonus question, and none of these options is the correct one. So actual answer should be none of these. Next question. We are given, in an electrical circuit, a battery is connected to pass 20 Coulomb of charge through it in a certain given time. The potential difference between the two plates of battery is maintained at 15 volt. The work done by the battery is. So basically work done in moving a charge is basic a formula, that is work done is equal to charge multiplied by the potential difference. So this is directly based on the formula. It says that our work is equal to charge multiplied by potential difference. We are given a charge of 20 Coulomb and potential difference is said to be 15 volt. So we substitute the value, we get this as 20 multiplied by 15, and this comes as 300 joules. Okay. So the correct answer is our 300 joules. Next question. It states that a charge Q is placed at one corner of a cube as shown in the figure. The flux of the electrostatic field through the shaded area is. So we are given that a cube is given and charge is placed at one of the corners. Okay. we want to use the Gauss law, but the Gauss law, the charge should be enclosed within the surfaces. That is the main condition of the Gauss law. Okay. You can say Gauss law it states that flux total should be equal to our charge enclosed divided by epsilon naught. Here the charge is at the corner, so we are given that the charge is located at the corner, and we want that one corner of the cube basically, and we want that this charge should be enclosed by, this charge should be ideally enclosed. So in order to enclose the charge, this charge is Q, we require that this particular corner should be shared by 8 cubes. Okay. So from here we can write that one corner of a cube should be shared by 8 cubes. And so basically we can just, because let us try to understand what he wants to say. If this is our cube, and for the sake of convenience, let us assume that the charge is here, okay, and we want to enclose this particular charge. Therefore, we have to draw the cubes. So one cube will be in this direction, and other cube will be on the top of it. So this will be our one cube, and another cube will be on the top of it, another cube will be in the back of it, and similarly we have to, you can say, generate the total 8 cubes such that this particular charge is within the Gaussian surface. So we can just draw here. One second. So this will be first cube, and another cube will be on the top of it, and there will be one cube which will be somewhere here, and so, and other will be on the back side of it. Okay. So this way this charge will be enclosed. Okay, so this is our front face, and from the back face we are also going to get our this, such that this point is enclosed from all the, you can say, surfaces, from all the sides. Therefore, we can say that one corner of cube should be shared by 8 cubes. Thus, we can write, therefore, only 1/8 of the charge is enclosed by the given cube. So you can say our charge enclosed will be equal to total charge divided by 8, and the flux, the total flux through the given cube will be our phi cube, and we can write this as our phi cube. Charge enclosed is q by 8 and divided by epsilon naught. So this can be written as q by 8, and we have this epsilon naught. But this flux is through the entire cube, and we are given that the charge is at the corner of the cube. So we have to remember that a cube has total of 6 faces, and if the charge is at the corner, the electric field lines are not going to pass through all these faces equally. So from here we can write that a cube has total of 6 faces, and we are given that the charge is at the corner. The charge is at the corner. Therefore, from here we can write that the charge is at corner. Therefore, the electric field lines do not pass equally through all the faces. Especially the flux through the faces which is touching the charge will be equal to 0, because the field lines will be tangential to the surface. So we can say that flux through faces touching the charge is equal to 0, because field lines are tangential to these surfaces. Tangential to the surfaces. And so we are total having 6 surfaces. So sorry, 6 faces. So 6 faces, 3 faces are going to touch the charge, and we are left with only 3 faces. Okay. So we can say touching the charge, 3 faces touch the given charge. So from these faces it has to be 0, and we are left with only 3 faces. 3 faces are left. So therefore each phase flux, that is our phi, will be equal to our 1 by 3 q upon 8 epsilon naught. So from here we can say our flux associated with each phase will be equal to q upon 24 times epsilon naught. So we get option 3 is the correct one. Three is correct. Next question. We are given two small spheres each of mass 10 milligram, are suspended from a point by threads 0.5 meter long. They are equally charged and repel each other to a distance of 0.20 meter. The charge on each sphere is A times 10⁻⁻8 divided by 21 Coulomb. The value of A will be given as, take G as 10 meter per second square. So we can just draw an approximate figure for that. And suppose this is the mean position and they are repelling each other because they are having same charge. This distance is given to us as 0.2 meter and each is having a mass of m and charge q. So let us suppose it is making angle theta with the vertical and there will be tension T, mg will be in the downward direction and there will be electrostatic force. Let us suppose that is a Fe. We can divide this T into two components and we are going to have this will be T, so we get this as T cos of theta and we have this as T sine of theta. So as this is, so we can just under equilibrium our horizontal forces, we can say under equilibrium we have our T sine of theta is equal to our electrostatic force, which is our K Q square, and let us suppose this distance is called as R square. And in vertical we can write our T cos of theta is equal to our mg. So if we divide these two, we are going to get sine of theta divided by cos of theta will be equal to, this will be our K Q square upon R square and divided by mg. And we need to find out the charge. Therefore, from here we can say our Q square sine theta over cos theta comes as tangent of theta and multiply by our mg R square and divide by K times, Q we need to find out. So divided by K. And we can easily find out our tangent of theta because we are given that thread's length is given the 0.5. So let me redraw the figure here. So this angle is theta. So this length is given to us as 0.5 and entire distance is our 0.2, so we can write this as 0.1. Therefore, tangent of theta will be equal to our 0.1 divided by 0.5, which comes as 1 by 5. So we can easily find out our Q now. We substitute values, we get this as Q square is equal to 1 by 5 multiply by mass is given to us. So this comes as 10 into 10 to the power minus 6. G is our 10, radius is our 0.2, sorry, distance is 0.2 r square, and K is our 9 into 10 to the power 9. So this gives us that our Q will be equal to 2 root 2 divided by 3 and 10 to the power minus 8. And we are given it is as A into 10 to the power minus 8. So one second. Oh, divided by 21. My mistake. Divided by 21. So we can just say that A upon 21 will be equal to 2 root 2 divided by 3. And so we get this will be equal to over A is equal to, this goes by 7. So this comes as 14 times square root of 2. And so value of A will be equal to 14 root 2. And root 2 is I think 1.414. So it will be coming approximately equal to, this is 14 into 1 point, I think this is 414 if I'm not wrong. Let me, and this comes as our, yes, and multiply by 14, this will be coming as 19.7. 19.7. So we can say our A is approximately equal to 20. So value of A is our 20. Next question. It states that two identical conducting spheres with negligible volume have 2.1 nanocoulomb and minus 0.1 nanocoulomb charges respectively. They are brought into contact and then separated by a distance of 0.5 meter. The electrostatic force acting between the spheres is dash into 10 to the power minus 9. So we are given that we are having two identical conducting spheres. So let us suppose this is a sphere A and this is a sphere B. Charges on them is given as 2.1 nanocoulomb and other one is minus 0.1 nanocoulomb. And then they are brought together. So it will be something like this. So this is our A and B, and then they are again separated. So this is our A and this is our sphere B. Now the distance between them is given to us 0.5 meters. We have to find out the force acting on them. So obviously, as soon as they are brought together with each other, they are going to, the charges, they should be at the same potential, so which will be resulting in the charge redistribution. So let us assume that this, we have our QA and this we call this as our QB. And so we can say that total initial charge So this is our initial condition and this is our final condition. So total initial charge, let us call this as Qi, will be equal to Qa plus Qb. So we get our Qi will be equal to, this is our 2.1 minus 0.1 nanocoulomb, giving us initial charge of 2 nanocoulomb. And since spheres A and B are identical, so this charge, total charge, will be equally distributed among them. So we are given that since A and B are identical, each sphere will have a final charge of, let us call this as Qf, which will be equal to our 2/2 nanocoulomb, which comes as 1 nanocoulomb. So final charge, let us suppose we call this as Qa prime and this is our Qb prime. Therefore we can say that our Qa prime will be equal to Qb prime is equal to 1 nanocoulomb. Now we can easily find out the force that is under final condition. Therefore we can say that of electrostatic force F will be equal to K, we have here Qa prime multiplied by Qb prime. Suppose the distance between them is our r, and this is our r square. We substitute the value, we get F is equal to K is 9 into 10 to the power 9, Qa prime and Qb prime is same, so this comes as 1 into 10 to the power minus 9 multiplied by 1 into 10 to the power minus 9, and radius between them is 0.5, so this comes as 0.5 whole square. And this 9 and 9 goes away, so we get this as 9 upon, this will be 0.25, and 9 upon 0.25 into 10 to the power minus 9, and this comes as 900 divided by 25, which will be coming close to, I think, 900. This goes by 3 and 6, should be 36. So we get our force F will be equal to 36 into 10 to the power minus 9 newtons. So value of this comes as our 9. No, sorry, not 9, but 36. 10 to the power minus 9 is already given to us. Next question. We are given the electric field in a region is given as E is equal to 3 E naught I divided by 5 plus 4 E naught J divided by 5 Newton per Coulomb. The ratio of the flux reported field through a rectangular surface area of 0.2 meter square, and the surface is parallel to YZ plane to that of surface area of 0.3 meter square parallel to XZ plane is A is to B. Then the value of A is, So here we are given electric field, and you can say that our electric field that is given to us is our 3 by 5 A naught I unit vector plus 4 by 5 E naught J unit vector, and we are having two surface areas. One is in YZ plane and another one is in XZ plane. Okay. So you can say that our surface area which is our YZ plane, parallel to YZ plane rather, is, let us suppose we call this as A1, which is given as 0.2 meter square, and this is Newton per Coulomb, and surface area which is parallel to XZ plane, let us suppose that is given as A2, it is given to us as 0.3 meter square. And first of all, because the electric field is nothing but a dot product, the flux is the dot product of electric field as well as our area, and there we are having a area is nothing inclusive of our unit vector. Okay, let me write it out. So we can say that our electric flux that is our phi is equal to our E dot A, or in terms of unit vector we can write this as our E, and we have this as dot A, and we have a n unit vector. Here n unit vector is our representation of our area vector. Therefore we can write our flux phi will be equal to A, we can take as common because it is now only magnitude. So this comes as electric field dot product with the unit vector. We need to find out the value of this unit vector. Obviously we have two areas, so we can divide this unit vector into two parts, and we say that surface parallel to YZ plane has a normal along x-axis. So we can say our n1 unit vector is equal to our plus j. Similarly, we can say that the surface parallel to xz plane has a normal along y-axis. So we can say our n2 unit vector will be equal to our j. Now we can find out the individual flux. So you can say that for surface area A1, the flux, let us suppose, is phi 1 will be equal to our area, and this comes as E dot n1 unit vector. Area will be also A1, and we substitute the value, we get our phi 1 area is given to us as 0.2, and this comes as electric field is our 3 by 5 E naught plus 4 by 5 E naught, and this is our dot I. So we can say that our phi 1 will be equal to, this comes as I j will be our 0, so remaining part is only I, so this comes as 0.6, 0.6 divided by 5 times our E naught. Similarly, we can solve for surface area A2. For surface area A2, we can say our phi 2 will be equal to, area is given as 0.3 and electric field is the same, which is our 3 by 5 E2I plus E naught I, and this is 4 by 5 E naught j and dot j unit vector. So we get our phi 2, this will be 1.2 divided by 5 times E naught, and we need to find out the ratio. So we can say our phi 1 upon phi 2 will be equal to, phi 1 is our 0.6 times E naught divided by 5, 1.2 divided by 5 times our E naught, and here our E naught phi cancel out, and this comes as our 1 by 2, and it is given as A by B. So from here we can say value of A is equal to our 1. So value of A is our 1. Next question. We are given that 512 identical drops of mercury are charged to a potential of 2 volt each. The drops are joined to form a single drop. The potential of this drop is equal to, and so we are having a small drop. Let us suppose its radius is r and the number are 512. They all are being combined to form a bigger drop, and let us suppose its radius is capital R. Okay. And the potential of each drop is 2 volt. Okay. And we can easily find out if the charge on the small drop is small q and the charge on capital drop is our capital Q, therefore we can say this total charge Q will be equal to 512 times small q. And we can also find out the relationship. We can say that 512 multiplied by volume of the small drop is equal to 4 by 3 volume of the capital drop. Here 4 by 3 pi and pi cancels out. So we get that our R will be equal to our, this will be coming as, let me write it still R cube, we can sort it out later, 512 times small r cube. And also we know that the potential of we can just write in terms of proportionality. So if we have potential of V, then this V potential will be proportional to charge oblique radius. And this is the general formula. So we can write that the new potential, because our one second. Okay. So if the potential of this larger is our V nu, therefore we can write that our V nu is proportional to our total charge divided by radius. We already know relationship between capital Q is our 512 times Q, and this also we have here small will be our small r, and this we have 512 upon 1 by 3. So this can be written as, from here we get, this will be 1 minus 1 by 3. So we get this as 512 2 by 3 Q upon R. And this Q upon R is our old potential. So V old is given as 2 volt. So we get our new potential will be equal to 2 times, we have this as 512, and this is our 2 by 3. And we can write this will be our 8 raised to power 3. So this comes as 8 raised to power 3, and this is 2 by 3, giving us cube goes by 1 by 3 and 8 square 64. So this comes as 2 times 64. So we get our new potential will be equal to 128 volts. So we have this as 128. Next question. It states that the potential energy U of a diatomic molecule in a uniform is a function of, the potential energy U of a diatomic molecule is a function of dependent on R, that is intermolecular distance, as U is equal to alpha divided by R raised to power 10 minus beta divided by R raised to power 5 and minus 3, where alpha and beta are positive constants. The equilibrium distance between two atoms will be 2 alpha divided by beta whole raised to power a by b, where value of a is equal to. So we are given that equation of a potential energy is given to us. So we are given that energy U is equal to alpha upon R raised to power 10 minus beta upon R raised to power 5 minus 3. And we have to find out the equilibrium distance. And under equilibrium distance, we can say that your energy has to be minimum. So you can say at equilibrium distance, potential energy should be minimum. Or we can say our derivative of energy with respect to distance r should be equal to 0. So we simply derivate it. So we get this as du by dr will be equal to d of dr, we have this as alpha upon r raised to power 10 minus beta upon r raised to power 5 and minus of 3. And this gives us minus 10 alpha r raised to power minus 11, and this comes as plus 5 beta r raised to power minus 6, and we are going to set this is equal to 0. Du by dr is equal to 0, which gives us minus 10 alpha r raised to power minus 11 plus 5 beta r raised to power minus 6 is equal to 0. Now it's a quite simple part. We get this as our 5 beta r raised to power minus 6 is equal to 10 alpha r raised to power minus 11, and we are given in the format of distance, so we need to find out r. Therefore we can write this will be equal to this goes by 2, and we have our this is our 6, and this will be left with 5 because both are minus. So we can say, and this will be r raised to power minus 5, so we get this as beta r raised to power plus 5 is equal to 2 times alpha. And from here we can write our r is equal to 2 alpha divided by beta whole raised to power 1 by 5, and which is given to us as 2 alpha by beta whole raised to power a by b. So therefore we can say from here that value of a upon b will be equal to 1 upon 5. 1 second. 2 alpha upon beta a upon b. Yeah. So this gives us that the value of a is equal to 1. So this completes the part 1 for the year 2021, and in this part 1 we completed 10 questions. So remaining questions will be dealt with part 2, and if required we will also do a part 3 covering the mains as well as the advanced questions. This completes the first part of 10 questions. Thank you.